Today we are starting the new lesson, and this lecture is actually sort of the central part of this course. It's a very important, and that's because this is a very important topic that has a lot of applications. A lot of times it has applications that you don't even know about. So a lot of times you're literally clicking buttons on your computer, and there are systems of linear equations solved underneath before actually something happens on your computer. Whether it's actually just that you're attempting to solve an engineering problem, or it's actually something that is related to the functioning of your computer. So linear systems, or a lot of engineering problems, come down to solving systems of linear equations. So we will spend quite a bit of time. For you, first we will actually introduce the linear systems themselves and certain definitions related to them. Then we will move on to actually how to solve for linear systems. So we will be doing that manually. And in the end, we will learn how to program as well as how to use built-in solvers that are there in MATLAB already. So just to give you an idea of where we are in the course, so we have now finished the topic of root finding with both different types of methods. So we overviewed over 5 or 6 methods. And today we are starting linear systems of equations. We will only touch upon nonlinear equations, and then we will move on to curve fitting, numerical calculus, and ordinary differential equations. So just a general definition, what is a system of linear equations? I typically have a number of unknowns. In this general case, they're represented as x1, x2, all the way to xn. So I have n unknowns here. And then I have just linear coefficients, just numbers. So I have a11, that's a number, x1 plus a12, x2 plus all the way to a1n, xn is equal to b1. That is my equation 1. Okay. Then I have a very similar equation 2. I'm just changing this numbering system so that I can actually denote this second equation in the most general case and all the way to the nth equation. So when I actually look at this a little closer, I see that these A's, I can actually put them in a matrix. So I have matrix A that has elements A11, A12, all the way to A1n. That's my first row. Then my second row is A21, A22, all the way to A2n. And finally, nth row, AN1, and so forth. So I have, in this case, a square matrix. And then I have a vector B of sort of right-hand sides for these equations, b1, b2, all the way to bn. And if I look a little better, this first row, and we review what we did about matrix algebra at the very beginning, this is basically a scalar product of my first row of matrix A and vector of unknowns x1, x2 to xn. This is the second row matrix times my vector x1, x2 through xn. So basically I can represent this system as ax is equal to b, where this is my matrix vector multiplication ax. Okay? So this is precisely why we actually went over review of matrix algebra. Okay? So here's one example where you might actually not know, but there is a lot of linear equations solved. So if this is my Velborg, this is just a half of the Velborg as is often represented in numerical software. If you actually have, so anytime you're in subsurface, you will learn in geomechanics later that you have 3 major stresses acting on you. And these stresses are orthogonal to each other. So there is a vertical stress that is basically the overburden on top of me. And then there are 2 horizontal stresses, and we call them typically sigma h and sigma capital H as in maximum stress and sigma small h as in minimum stress that acts in horizontal direction. And because of that uneven action, the larger the difference between these horizontal stresses, I might have a higher chance of fracturing around my wellbore because I drilled a hole and there's no support here. So basically the stresses here overall, even though I have compression from all sides, since I drilled out the cylinder, there might be tension happening here. Okay? So that might split away the rock. Rocks are not well suited to withstand tension. They are built in compression. The moment you try to pull them away, you're going to break them real easy. So in this case, you might actually have splitting of the rock because of the tension happening here, and that's essentially hydraulic fracturing, and it happens with the help of the pressure in the water that we are injecting. And you might actually have too much compression basically at the azimuth of the minimal stress, and rock will crumble away and go away. So that is a damage around the wellbore as well. It's called a breakout. So obviously we want to study this problem, and we want to figure out, well, when it is that I have too much pressure in water, so I shouldn't go above that so that I don't cause these problems. Okay? Now, if the method in solid mechanics that is actually solving this is called finite element method, and after some manipulation, what it really comes down to is solving a linear system. Okay. So you put in your boundary conditions, your stresses, and so forth, and then there are equations, linear elasticity, that are solved. But what it really comes down to find the stress distribution everywhere, I have to actually solve the system of linear equations. So it's not necessarily immediately obvious, but that's what a lot of numerical methods that are solving physical problems, they come down to a system of linear equations, because that's something that is the simplest to solve. The moment we have the nonlinear system of equation, so for instance, let's say that you put squares here, x1 square, x2 square, xn square, those are nonlinear equations, then we're in much trouble. Those are difficult to solve. So we typically, in the end, linearize them anyway and solve for the linear system of equation. So linear systems are everywhere. This is one important example that is important in petroleum engineering, but everywhere else as well. Finite element methods are very common methods in engineering. So this is one motivation. So let's now go over some notation that we will need for solving these systems. So for one, in order to actually have a solution, I have to have what's called enough independent equations, meaning that I have enough information to actually solve the problem. So in the case of a 3x3 system, I will have to have to solve for 3 unknowns, I will have to have 3 equations to solve for it properly. If I have more equations than I actually have unknowns, I might actually have an overdetermined system. So this would be the case in this particular case. And if I have too little, so in this case I have 4 unknowns, but I have 3 equations, that is not enough to solve the system. So my system is underdetermined in that case. So let's say that I have two equations, x plus 1 is equal to 1, and 2x plus 2y is equal to 2. Do I actually have a properly determined system where I can solve for both x and y? So this is the case where actually I formally have 2 equations, but one is multiple of the other. So my second one is 2 times the first one, and in terms of the equation, it doesn't really bring any new information. So I'm effectively down to only one equation, x plus 1 is equal to 1, and 2 unknowns. And what's the solution to such an equation? What's x plus 1 is equal to 1? What is that geometrical? In a 2D? Circle would be x squared plus y squared equal to 1. So circle is nonlinear. What's linear in 2D? a line, and that line is y is equal to 1 minus x, right? So line has infinitely many points, so I have infinitely many points. They're constrained, they're on a line, but I have infinitely many points solving. It's not solving. Those are my solutions. I don't have one solution. So the question is, what does it mean to solve the system, right? I might have infinitely many solutions. I'm typically looking for a unique solution where I want just one point. So how will I get geometrically just one point? If I have two lines, what do I need to do? Intersect them, and I'm going to have a solution. So geometrically, when I have a 2 by 2 systems, I'm actually intersection of two lines. So my unique solution, if it exists, it's an intersection of two lines, and these equations that we look at are actually solutions to them. So these two lines do not intersect. They're actually the same here, but they could also be parallel. So in that case, they will not have a solution. Okay. So here are some special systems. The most simplest one that one could actually solve is the diagonal system. So in diagonal system, I will have a diagonal matrix of coefficients. So all of my elements are 0 except those that are on diagonal. So in that case, I have very simple system. I will have system that is, in this case, C1x1 is equal to some right-hand side, then C2x2 is equal to something else on the right-hand side, and so forth. And that's simple to solve. We will often, mathematically, if I actually had so-called matrix inverse, okay, that is a matrix that when I multiply my matrix, I will get identity matrix. That is, if I actually have that matrix inverse, then I can actually easily find the solution. So I will just multiply with inverse, so my solution for AX is equal to B will be A inverse B. Okay. So that makes it easy to actually solve, if I actually have an inverse. But however, often I actually don't have an inverse, and this is a mathematical mistake here. So this should be, there we go. So we know that in matrices it is important in which order I multiply them, so I should have multiplied here from the left side. So A inverse A, X is equal to A inverse B, which means that this is the identity matrix. Identity matrix times any vector is that vector itself, so X is equal to A inverse B. Most often, however, I don't have an inverse, and actually finding an inverse is a problem that we can formulate as a system of linear equations as well. Symmetric matrix, symmetricity matrix, symmetricity is important for actually knowing that I have a solution and knowing that my numerical method will converge to a solution. So in this case, we actually have a matrix where all of my, if I did a transpose of the matrix, I would get the same matrix. So such matrices are symmetric. So we see the same element sort of across, mirroring across the diagonal. So I have -2, -2 here, -1, -1, -1, -1. And then a couple of more. These are just definitions that we will use later on once we get to the numerical solutions. So so-called tri-diagonal matrices, they have elements only on diagonal, 3 diagonals. I could actually have 5 diagonals, 7 diagonals, and so forth, but tri-diagonal matrices are most common. So basically, all of the other elements here are 0, and I have something living on diagonal. And then so-called positive definite matrices have all of the positive eigenvalues. Now, when I say eigenvalues, have you all taken differential equations and mentioned what eigenvalues were? No? Well, we'll get to that then a little later. We'll define them a little later. It's not a big deal, but basically, eigenvalues for a matrix are such values where I can find vectors. So I typically have to have eigenvector and eigenvalue pair. And for that pair, it's true that A times, let's say that I have lambda as an eigenvalue and x as a vector. Ax is the same as lambda, which is a scalar, times x. So multiplying my matrix and the vector is not resulting in some vector that is anywhere. It's resulting in a vector that is lambda x, so I'm just stretching along x. So my action of the matrix on my eigenvector is just stretching it along its own direction, right, without sending it to some different direction. Okay, so those are called eigenvectors and eigenvalues, and they have theoretically a lot of applications. For instance, the stresses that I mentioned. So typically you will have stress field in 3 dimensions described by a matrix. And my major stresses, my vertical stress and those 2 horizontal stresses in subsurface that I mentioned, the minimum in horizontal and the maximum in horizontal, those 3 stresses are actually eigenvalues of my stress matrix, the stress tensor. And they're very important to find because among those eigenvalues, I will actually find the minimum and the maximum, so the extreme values of stress, period. So if I have a stress field defined by a matrix, then for instance, the eigenvalues of that stress field will tell me what are my minimum and maximum stresses. Those are extremely important for a petroleum engineer to know again, because the difference between the minimum and maximum stress that I have basically tells me, am I fracturing and how am I fracturing? Am I having a well-bore breakout, or am I not having a well-bore breakout? And ultimately tells me, am I collapsing my well-bore? So obviously we'd love to know. Okay? So basically eigenvalues, they're possibly like when you learn about them in differential equations, there will be this sort of relatively term, esoteric term, like why are we learning about this? It's just this mathematically cute. It's not just mathematically cute, it's very real for petroleum engineers to know minimum and maximum stresses that are acting on you in subsurface and 3 kilometers long. Okay? Very important. So don't dismiss eigenvalues as something that just, oh, the professor in math wants you to know. Okay? So they actually do have very real importance in a lot of fields, not just in petroleum engineering. Another one is signal processing. Okay, so any signal that you have, it could be your pressure measurement, it could be any measurement in the lab, okay, is typically a wave. And the way we look at that wave, we will actually analyze it for eigenvalues, which will tell you the dominant frequencies. And then typically you can reduce storage for your signal down to 5 dominant frequencies as opposed to storing hundreds of them, whereas most of them are noise. So you just go and pick the largest ones, you look for those extremes, and those are the ones that are important. So that's also how any file compression works. You're typically saving only what's important, and the analysis that goes into it is essentially eigenvalue analysis, without going into too much detail. So there's a lot of importance about eigenvalues. Anyway, I can actually tell that I have so-called a positive definite matrices that has all positive eigenvalues, so I'm not going into negative values. If I look at my elements on the diagonal, and for instance, let's look at the first row. A11 has to be larger in absolute values than the sum of the absolute values for all of the others. And then my A22 has to be larger in absolute values than sum of all of the others' absolute values, and so forth. If that's true for every row, then I have a so-called positive definite matrix. So that's one, and actually a rare test where I can actually just look at the matrix and tell whether it's positive definite and it has positive eigenvalues. And again, if I'm in subsurface, below 100 meters down, my eigenvalues, that is the stresses, better be all positive. In geomechanics, compressive stresses are positive. If I have some sort of tension, then I'm having fracturing happening. So typically in a normal undisturbed situation, I will actually have my stress tensor will have eigenvalues on one side, and that sign indicates that I have compression, not tension. Okay. So if I'm pulling things away, that's tension. If I'm compressing them, that's in geomechanics, that's positive. In linear elasticity, that you might learn in solids, tension is positive, compression is negative. Any suggestions why would that be? So, for instance, in one branch of solid mechanics that is typically dealing with bridges, okay, I will call my tension stresses positive, in compression negative. Whereas when I go in subsurface in geomechanics, I will do it the other way around. Why are those two fields having the opposite conventions?
Because like bridges, it's mostly under tension, so tension will be positive.
Right. So you don't want to deal with negative numbers. In geomechanics, below 100 meters, it's mostly compression. So I don't want to deal with negative numbers. So beware of that. Because right now most of you have done solids. Huh? Or you're going through it right now? Yeah, so the next thing is geomechanics, so we'll kind of learn the opposite side. All right, so those are the major stresses are my eigenvalues. This is why I'm actually telling this story. All right, so let's go back to small systems of equations and just do a little bit of geometrical feel for the solutions of my systems. Let's say that I have 3x1 plus 2x2 is equal to 18. And minus x1 plus 2x2 is equal to 2. So if you have a piece of paper, can you please quickly solve this? Well, there's a solution given, but it's good if you actually go through it yourself. If I just go through it, you'll feel like this, and half of you will be asleep. So let's actually just solve it. If you're bored by this system, give yourself different numbers, okay? Or come up with a way to solve this that is different than what's written on the board. How's that? Use a different approach. Everybody got a chance to find the solution? Solution should be 4 and 3. So just to basically, we know how to solve this algebraically, and hopefully we find x and x2, x1 and x2 that satisfy both of these equations. There could be situations where that's not the case. So I either cannot find just one x1, x2, I might actually find a lot of them. That's the situation I commented before. Or I might find none. System has no solution. That's in the, we will actually look at those cases graphically. So, for instance, if I actually look at the graphical solution, I can show this first equation is basically x2 equals to 18 minus 3x1 divided by 2. And I can plot that. All I need is to find 2 points on this line, and I can basically join them by a line. And this is the line right here. Okay? I can also plot the second equation as a line, and that is the line here, and then graphically my solution for 3 is right here at the intersection. Now this line is 3x1 plus 2x2 is equal to 18. Can you venture a guess what would the line that is going like right here, what would its equation be? For instance, so basically the same sum, 3x1 plus 2x2, for larger x2s and larger x1s would be, for instance, 25, not 18. Okay? So the line right here, or 19, or 21, or you name it, a larger number, I don't know, I don't have the ruler here to precisely find out. So basically, those two lines are parallel. And obviously, I don't expect for the same couple of numbers, x1, x2, to satisfy both. This sum, 3x1 plus 2x2, cannot be both 18 and 25 at the same time. And therefore, in that case, I will not have a solution to my system. So there are systems that obviously don't have solutions. And the second situation is where basically if I just say, well, 6x1 plus 4x2 is equal to 36, I didn't say anything new. Okay? Because for all of x1 and x2s, for which that is true, it is also true that 3x1 plus 2x2 is equal to 18. So I know algebraically that I can just multiply an equation with any number other than 0, and I will get an equation that states the same piece of information. Okay? So we can also, then in that case, both of the equations would basically collapse on the same line, and I would have infinitely many solutions. So all of x1s and x2s on that line would be a solution of that system. So basically, this is shown here. So again, if I have two parallel lines, I don't have a solution. I might actually collapse onto the same line. In which case I'm just multiplying one equation by a number. I could also be very close. Okay? So if you remember our discussion on how numbers are not super accurately represented on a computer, I can imagine how these two things where I have lines that are really close could actually be interpreted as the same by a computer simply because my resolution for storing the number is not good enough. So there are some problems, and these systems are basically, we call them ill-behaved. Okay, so mathematically there should be a solution, but numerically it's difficult to find because of the precision with which we are storing the numbers. Okay. So we interpret that, or in definitions we say that this matrix that is corresponding to the system should be non-singular. In that case, so I should not have certain rows multiplying each other being defined as independent rows, and in that case, I will be able to find a unique solution. Okay, I see you on Monday.